Welcome to the session. First speaker, Preusker.
Yeah, thank you. Okay. Good afternoon, everybody. I will start this session with the topography of Mercury. Start with the basics. I'm talking about MESSENGER data. So MESSENGER was launched in 2004. We had flybys in 2008, two of them, and in 2009. We already did something for topography with flyby data. You can see it in the Obers et al. Paper 2010 and Preusker et al. Paper in 2011. Then we had an orbit insection in 2011. And then we had almost 4 years orbit operation. The measurement goal was the topography, global mapping. We have two main techniques. We have laser ranging and stereo imaging. And due to the eccentrical orbit of the MESSENGER spacecraft, the laser altimeter was somehow limited only for the northern hemisphere. Therefore, we need something or stereo imaging for the southern hemisphere. The camera on board on a MESSENGER is the MDIS camera. It's there is a narrow-angle camera and a wide-angle camera. Both are somehow complementary, that you have the narrow-angle camera for the southern hemisphere mostly, and the wide-angle camera for the northern hemisphere, that you can have somehow the same image resolution for the whole body. And this in not only in one global coverage, so in multi-coverage. And with a resolution better than 200 meters or 250 meters. So our motivation, clear. We want to have a global high-res topography base map for Mercury. So this should be the complementary base map for MLA in the Northern Hemisphere. We need this for all kind of stuff. So we need it for geomorphologic analysis. We need it for precise auto rectification and many more things, and of course for the preparation of Bepi-Colombo. Our processing strategy is here. We have divided our surface in 15 tiles. You can see it here. So each quadrangle contains or is covered by nearly 10,000 images. And from that, we have almost 20,000 stereo image combinations, and some quadrangles more and some quadrangles less than that. The Northern Hemisphere quads we're using for co-registration with MLA, and we have used these for the determination of the rotational state of Mercury. You can see here there's a paper from Alexander Stark, which is what I recommend to read. And when we complete all these quadrangles, then we will combine them to a global shape. We start with the H6 quadrangle in earlier times, so it was in 2014, 2015, and it was chosen as a prototype to show how we can get or can have a quadrangle DTM. This was delivered in 2016, so last year, and published, also the whole work was published in 2007, this year. About the methods. So on the left-hand side, you can see our methods, and here you can see an example from the paper. First, we start with the identification of suitable images. So, and this is depends on these parameters for the illumination and the viewing conditions for the images. And one essential parameter is the illumination. Pardon? Perfect. I don't like it. Okay. One important point is the illumination conditions. So the illumination differences. So we need for the image correlation, we need images which are nearly similar, so that it's they can perfectly matched. The stereo angles are needed for the reconstruction. Incident emission angle, phase angles are similar. We need good illuminated images for correlation and so on. So after here for H6 we have 10,000 NAC images and WAC images with an average resolution of 150 meters and about 20,000 stereo image combination. So with at least 3 images each in these combinations. Then we start with sparse image matching. This is needed for the bundle block adjustment. So every image is somehow connected over points, and then we use these images and the control points or the type points to reconstruct or to improve the nominal position and pointing of the images. And here you can see for H6 we could improve the surface point accuracy from 800 meters to 50 meters. After this, we using high dense multi-matching, image matching, and collect pixel by pixel wide in each image and collect 45 billion type points. And in the end, we had somehow 6.3 billion surface points. Then we generate a surface point from this and produce a DTM, so a 2.5D presentation. And we choose lateral spacing of 192 pixel per degree. That's 22 meters per pixel. We had a vertical accuracy of 30 meters. So it's nice and perfect. Here you can see it in full res, and this was delivered in 2016, so it's available in PDS. We did it again. Yeah, we had a request from the project if we could deliver other quadrangles, and we choose the H3, H4, 5, and H7, and this was also processed and delivered this year. And it's available under PDS. Here you can see the link. So, yeah, what's about the southern hemisphere? So we start with the southern hemisphere. We have H11 to H15, and I will start with H11. So H11, we have in total 6,000 NAC images and only few WAC images. With a resolution of 170 meters per pixel. We collect 30,000 stereo image combination. From this, we had almost 300,000 type points, 60,000 surface points, and we could improve the accuracy by bundle block adjustment from 750 meters to 40 meters. We collect a lot of type points for the reconstruction, and you can see we have only few places where we have gaps so far. So it's not completed, but we are still in a pipeline that we expect that we are finished pretty soon. The vertical resolution of these quadrangles is about 30 meters. Then we have the Michelangelo, the H12. It's similar. We have almost 5,300 NAC images, only a few WAC images. The image resolution is a little bit less than for the H11 quadrangle. We have a little bit more stereo image combination. Here you can see we have also used a little more type points for the reconstruction. The accuracy is a little bit less than for H11, but it depends on the images and the stereo geometry. We collected billions of type points and computed billions of surface points. Here you can see the Beethoven basin. It was also shown in I guess in a EPSC 2012. Yeah, the vertical resolution, vertical accuracy is about 35 meters. It's in the same manner. So the next one is age 13. Age 13 is it's quite similar. You can see we have almost full coverage. Here you can see that there are some parts where we have somehow missing stereo combinations. So that is the next step I will go into to look into the gaps and how can I fill these gaps with sufficient stereo information. The accuracy is almost the same for the like the other ones. So we have 30 meters in vertical accuracy. And also these 192 pixel per degree spatial lateral spacing. And last but not least, oh no, that's not, it's one, it's age 14. It's the same. Here you can see the Rembrandt basin. It's also published in the Waters et al. Paper in 2015. That is prominent because of the scarp you can see here. We have also the same situation, billions of surface points and tie points. Almost the primary instrument was a NAC image or the NAC camera, and the vertical resolution accuracy was 35 meters. And the last but not least is Bach, is the H15, the South Polar quadrangle. Here we have a little less than for the other quadrangles. It's a little bit smaller. 3,400 NAC images, no WAC images, because the image resolution we only took images with less than 300 meter per pixel. We have a little bit less than stereo image combination, but a lot of tie points we have used for the bundle block adjustment. The accuracy goes down to 30 meters. Vertical accuracy is pretty high, 25 meters. And we have a lot of tie points. But you can see here's some gaps near the pole, and I'm not sure if we can fill these because permanent shadowed terrains. So, but these kind of gaps will be filled in the next steps. So my outlook, in conclusion, we have successfully delivered 4 quadrangles to PDS. The Southern Hemisphere quadrangles will finalized until this year and I guess delivered promptly. Remaining quadrangles are planned to be ready next year, and we hopefully can finalize the global topography map for Mercury in 2019. Thank you very much.